All right, so this is 9.3. We're going to be talking about doing statistical significance testing about a population mean. Remember, we're going to check our conditions for a mean. They'll be the same as the conditions for means and confidence intervals. We're going to conduct a one-sample t-test about a population mean. We're going to construct a confidence interval to draw a conclusion about a two-sided test about a population mean, and perform significance tests on paired data. So this is something we haven't done yet, but we're going to talk about doing it with paired data. Same thing as before, confidence intervals. We have tests of proportions. P, use Z values from a standard normal, right? So when we use a mean, we're actually going to use a T distribution like it says here, and that we learned in 8.3. So the same kind of rules and conditions will follow in statistical testing for means. This should get pretty usual for you. You've done it enough times now that you've done it with the proportions, you've done statistical testing with proportions, you did means and confidence intervals, now we're going to do statistical testing with means, and so it's becoming pretty much standard for you. All right, so here's our first example. It says, in an earlier example, a company claimed that to have developed new AAA batteries last longer than its regular AAA batteries. Based on years of experience, the company knows that regular AAA batteries last for 30 hours of continuous use on average. A simple random sample of 15 batteries lasted on average 33.9 hours with a standard deviation of 9.8 hours. Does this data give convincing evidence that the batteries last longer on average? Well, I'll tell you this, as soon as I read the problem, I do realize I'm going to have an issue because I have a simple random sample of 15. Remember, 15 is really small, so we need to actually we're going to have to look at the data, because the problem is going to be when I go to check the normal condition, just like with confidence intervals, if it's like 1 to 14, it can't have pretty much symmetrical with no outliers. It's no outliers and pretty much no skewness. Since I have 15, so 15 to about 29 means I still can't have any outliers, no outliers, and I can have up to moderate skewness, and the T is going to be okay. So I don't have that. They haven't told me that the population was normal, so that didn't work for it. I don't have a sample size of at least 30, so I'm going to need to look at these, or my normal condition is not going to be met. So let's see what they give us, but that's going to be something that as soon as I read the problem, I'm a little worried about. So they go ahead and set it up to find out we must perform a significance test. They say that the mean hours is 30. But we think that the mean hours is more than 30. They last longer. That's what we want to prove. They're asking you evidence that the batteries last longer on average, so that's how they knew the alternative was the mean is greater than 30, where mean is the true mean lifetime of new AAA batteries. Now, to check the conditions, here's where they're talking about it. The population is normal, or the sample size is greater than or equal to 30. We often don't know the population distribution, but if the sample size is greater than or equal to 30, we safely carry out the significance test. If the sample size is small, we should examine the sample data for obvious departures from normality, such as skewness or outliers. And that's really what we have to do here, because we have a sample size of only 15. So here it is. They actually give you, we don't know the population distribution of the battery of lifetimes. We need to inspect the data for any departures from normality. So here they are giving you the data. We can look at a dot plot, again, a box and whiskers plot, and a normal probability plot. None of them give a dot plot and box plots show a little bit of right-hand skewness, like it's getting stretched out a little bit here, but no outliers, so we're okay, and then the normal probability is close to a straight line. So we should be safe performing a test about the population mean lifetime mu. So here they are checking the graph and looking at the actual data. Independent, again, they check the independence 10 times N, so 150 new AAA batteries. It's reasonable to believe that there's more than 150 out there, so we're good. I'm checking our conditions. So here we are. Again, we're going to do this the statistical test, just like we did with proportions. You're going to have your statistic minus the parameter over the standard deviation, and that gives you a standardized test statistic. And so then you can use that in the chart, or you're going to be able to use that with normal CDF. So here, what's happening is that my statistic for my value is that 33.9 minus the parameter, which is 30, over the standard deviation of the statistic. And from our green sheet, we realize that the standard deviation of the statistic is the standard deviation divided by the square root of n, right? So this is my stat is here, my parameter is this, and this right here, okay, that formula comes from that. So we would do 33.9 minus 30 over, and they told us that the standard deviation was, oh, I don't remember, let's look real quick, 9.8. So it's going to be 9.8 divided by the square root of 15. And that's going to give you your standardized test statistic. Remember that that value right there is going to be a z-score, is really, you know, what you're getting. And then you're going to compare it, find the probability of getting that value or something more extreme, all right, you know, over here. So if I were to actually put that into the calculator, I'm going to take 33.9 minus 30, and then I have to take that and divide by 9.8 over the square root of 15. And I get a z-statistic of 1.54129. So if I go back to my picture, my z-score is 1.5429, and so what's the probability of getting this or something greater? That's going to be that normal CDF with my lower, oh, sorry, it's not a normal curve, just kidding. We're on a T-curve, remember, because we're dealing with the means. And since my n equals 15, I have a degrees freedom of 14, which means I'm going to use a T-CDF on the calculator, and then my lower bound is still going to be this 1.54, and my upper bound is going to be infinity, and then all you have to do is tell it the degrees freedom, which is 14, and it will do it for you. And then in a moment I'll show you how to look it up in the chart.